Pydata. So in order to break the ice a little bit, Amer is going to briefly introduce our company, maybe say a little bit about what it is that we do. And then Zach will follow talking about our backend and how Python is an integral part and it plays a central role throughout our stack. And then we'll get started. So you're going to need this.
I'm loud.
You are? Okay.
Yeah. No. So let's try this without a microphone because I know that I am pretty loud and my voice carries. As Diego mentioned, my name is Amer. We are from Pydata. Pydata is a Toronto-based startup, 2.5 years old now. My role at Pydata is I manage the integration between our retail client systems and our solutions. And what we do at Pydata is we work with a retailer to leverage their loyalty system to deliver a customized personal digital experience. What the hell does that mean? It basically means we build white label apps for retailers where customers have access to the retailer's full product catalog, receive targeted offers, and have product recommendations. The goal is to deliver for each user or customer product combination, we deliver a score. And right now, that does set us a little bit apart from the competition, and that competition really concentrates on targeted offers. So the problem with recommendation is why you're here today, and is very prevalent in everything that we do day to day. And everything that you see here, we apply in a production environment every day. And our backend is purely Python based, and to hear a little bit more about that, Zach is going to give a scope of our stack.
Hi everyone, I'm Zach Howard, and I'm a sort of back-end engineer at Pydata. And yeah, so I'm going to talk to you about how we have Python deployed in a recommendation system, deploying a recommendation system in our live environment. Python is a critical part of our backend. It is entirely Python, actually, and so it does everything from handling mobile requests to data persistence to the recommendation engine. We use Flask to handle our mobile requests, which is basically a minimal web framework, similar to Django, but more modularized. We use SQL Alchemy to query our relational database, and we also have a Mongo instance that we query with PyMongo and MongoKit. And then we finally have the recommendation engine, which is running on NumPy, Pandas, for the and scikit and LTK, and that's sort of the training and estimate part. And then we use Pytables, which is sort of a local cache of the database for performance reasons, and it also caches intermediate results in the training algorithms. So the main interface for the recommendation engine is Celery, which is an asynchronous task library. And that what allows us to do is it affords us some concurrency if we need it in computing the recommendation results, and maybe we're also formatting our API responses or something at the same time so we can have a higher throughput. So yeah, that's it.
Cool. Thank you guys for that. All right, so about logistics for this tutorial, what you see up there are the instructions to get set up. If for some reason you are not able to set up a local environment with those library versions that we specify in there, just come and grab us. Actually, Zach and Amer are going to be roaming around the room and can help you out, solve any problems that you might have. I should mention, there were some people asking me about tables, so Pytables and the HDF library, and there were some problems setting that up. We have decided to make the Pytable section something that is a bonus towards the end of the tutorial for things that you will complete on your own. And the reason for that is because we wanted to include more advanced pandas. We think it's more core to the recommendation problem. So in that way, we also get rid of the HDF problem, and if you guys basically have NumPy and pandas, then you're already good to go. There was a question about that before, so.
Sorry, just to add to that, if you do still want to have tables installed and you want help with that, we can stick around after the tutorial and help you do that.
Yes. Okay, so what we're going to do for number 2 and 3, there's some files that you're going to need, some data files, and there's also a digital handout for you to follow along with the presentation. So the handouts are in the PDF exports subdirectory of the repository, if you've checked that out. If network is being not very reliable at the moment, we have a set of 10 USB keys going around, so just grab Just grab one from Zach there, and you can get the files. Everything is contained in there, both the handouts and also the data files, okay? Are there any questions about that or any problems?
Oh, and the electrician is coming around in 10 to 15 minutes to actually hook up the power bus. Yes, sir.
Yeah, continue.
Yep.
You have some instructions to download this and compare it, but if you don't have it, then just all the data and the outputs.
So, as a means of systems check, if you open the PDF export subdirectory and you go to the questions PDF file, you will see something that looks like this, which is actually an export from our notebook. Whether you're running on a local environment or using IPython or using even a notebook, this is basically how you can check that everything is ready for you to go and to get set up for this tutorial. If you can execute those 3 commands, sans the find and the tables, because we just said we're not going to need that, if you're able to import NumPy and if you're able to import pandas, then you should be good to go. And I'm just showing a directory listing there for the session that you're going to be working on. Those are the files that you should have. So your directory structure should look like that. If you've cloned a repository, that's exactly what you will get. And if not, you can just grab a USB key from Zach, like we said before, and that should get you an environment looking like that. Yes, question? Yes. So the question was, if you've checked out the repository, do you want to be in the master directory, which is where you unzip the repo? The answer to that is yes, because that will give you access to the files from that location. Okay? So are there any questions about that? We really want everybody to be able to follow along. This tutorial is going to be highly interactive. What we're going to do is we're going to present a few concepts, and then we're going to throw some questions at you, and then we're going to repeat that process. And toward the end, what we're going to try to do is for a few of you to come up and show some of the answers to the more complicated problems. And I'll talk a little bit more later for what's going to happen in the last hour of the tutorial. Okay? So another thing I would like to mention is that if for some reason you have not been able at all to set up your local environment, maybe you have an old version of Xcode, or you forgot to download the developer tools if you're on a Mac, or you don't have a compiler if you're on Windows or whatever it might be, and that would be a huge download for right now. Zach here has set up a pretty nifty tool that you can access by going to this URL, pycon.unata.com. Let me mention that before I tell you how to get started with this hosted environment is that let me tell you that if you have a local environment and it's working, then we recommend that you don't use this, especially because you'll be competing for the resources of the server. It's a large server, but still you'll be competing for resources on the server against the other people that don't have a local environment, so you might as well give them priority if you already have something working locally. So the way this works is that if you go to that URL, pycon.unata.com, and you enter a username, we recommend using first name and last name, and enter the password, which is Pycon, all lowercase. That will drop you into a personalized directory on the remote server, and it'll spawn, if it works. I'll try once more. Oh, it could be loading still, maybe?
You get a 404 not found, just refresh it, because sometimes it takes a bit while for the notebook's able to boot up. So the redirect isn't catching it.
Okay, so it should redirect you to a port that will be personal for you, and it'll spawn an instance of the IPython notebook. Okay? So if you're familiar with that, it'll basically just be a web-based interactive session with cells that you can evaluate, with code cells that you can evaluate. So what we have done for you is this personalized directory that is created in the server already contains the notebook version of the handouts, of the digital handouts that you have as PDFs. So for example, if you click on the questions one there, it'll bring up something that looks exactly like this, okay? And the environment there is already set up. I think that the shortcut to execute code is Control-Enter. Whenever you're typing something into a cell, you can just Control-Enter and it'll run it. And you can use that to follow along with the questions. Okay, are there any questions about that? Yes? Yeah, so it might be that since I'm saying this and everybody's accessing it at the same time, it could be a little slow. Zach can probably take a look over here and see if he can help you out with that. So with those logistics out of the way, I think that, yeah, I think we can get started. Are there any questions about that?
Just a few minutes as there's still some.
Okay. Yes. Yeah, so the question was the find command over there. Ignore that because that is IPython specific. Oh, it is. Okay, so if the question was about find, which is the last command there. If you're using the hosted notebook and you want to make sure that your files are okay, you can just use the ls magic, which is built into IPython. That should give you a directory listing, which is an alternative to find if find is failing. Okay? Okay. Were there any other questions? Yes? Yeah. So the question was, how do we get started on the remote setup? So I'm going to open up a new tab here, and if you go to that URL, pycon.unata.com, it'll be a bit slow, but this is what you should see. And using your first name, last name as your username, and Pycon as the password, or all lowercase, you will be dropped into a personal directory with a remote environment. Were there any other questions? We have some more people showing up. Okay. If you have any thought, or if you're here, then that's already set up. Yeah. So the question was, do we need anything else besides NumPy, pandas? Do we need matplotlib? That's already set up in there, even though we're not going to use it. So that's already set up in nthought and in the hosted notebook as well. Okay. All right. So we're going to give a couple of minutes for the new people to set up. I'll just repeat some of the setup stuff for the people that just show up. Okay. So what you're seeing here, for those of you that just joined us, what you're seeing here are the setup instructions for the tutorial. There are some specific library versions that you're going to need, and again, we recommend that you have a fully functional environment in your local laptop. There's also some files that you're going to need, all of which you can obtain from a repository on GitHub, or you can grab one of the USB keys from Zach and download all of the files from there, if the network is failing for whatever reason. Once you clone our repository, you'll be able to access the digital handouts in the PDF exports subdirectory. There's two of them. One of them is called Pycon PDF, which is the main presentation. You can use that to follow along. The other one is called Questions PDF, which contains the questions that we'll be throwing at you as we interact in this mode of presenting and then going to questions. And lastly, if for whatever reason it has been impossible for you to get set up locally and you can't install the libraries, or you don't have a compiler, or you're just running on an older system, we have set up a tool that is not bulletproof, so it could fail, but it's a fallback option for those of you that haven't been able to set up an environment locally, that we call Pydata. This is something that Zach put together. You can access that by going to pycon.unata.com, and by choosing a username that is your first name and your last name, no weird characters or anything like that, because it might crash it, please. And then the password is Pycon, all lowercase. Once you hit Let's Go there, it'll drop you into a personalized directory, and it'll redirect you to a different port on the server. And what you will get there is an IPython notebook instance, which is going to look exactly like that, hopefully. If you click on the questions notebook, that will open up the notebook with the question set, which is it should look exactly the same as the PDF that is called Questions PDF, only that it will be an interactive environment. So just to rehash that, there's two options. You can work on your local environment, or you can work on this hosted setup. We recommend that if you have a local environment, please do not use the hosted setup. Otherwise, you will be competing for resources on the server, and it is more likely that it'll crash. So let's leave that for the people that have had trouble setting up only. Okay? Well, are there any questions about that? Have people been able to get set up? Okay. All right, great. Glad we made it through that. So a beginner's introduction to Pydata. What we're going to do is we're going to get started with the recommendation problem, and then we'll go back to the agenda that we have for today and talk more about what it is exactly that we're going to do. So the more theoretical part, so to speak, is at the beginning, and we'll include some more formulas toward the end. But I think it's important to get familiar with what the problem is first, and then we'll try to apply some of the Python scientific libraries to tackle that. Okay? So first of all, I want to make sure everybody can see the text, or at least that you're following along with the digital version locally. So can everybody see you, or do you have your copy? You're all set up with that? Okay. I'll take that as a yes. So the recommendation problem. Recommenders have been around since at least '92. Today, whenever we say recommendation engine, it's like a buzz term. It's everywhere. And we really see different flavors of that throughout different verticals. We think of Amazon. We think of Netflix, Facebook, Last.fm. What is it exactly that they do? So I've gathered here 4 definitions from the literature. I should mention as well that at the bottom of this notebook there's a list of references, so that credit is place where credit is due. So I recommend that you check that. But a few definitions from the literature here. In a typical recommender system, people provide recommendations as inputs, and then the system aggregates and directs those to the appropriate recipients. Collaborative filtering was introduced in '92 in this paper, and it simply means that people collaborate to help one another to perform filtering by recording the reactions to documents that they read. The reason why this is talking about documents is because it was in the context of a system called Tapestry that was published back then. A paper that I really recommend as a good entry point into the literature, this paper has about 200 references or so, says that in its most common formulation, the recommendation problem is reduced to the problem of estimating ratings for the items that a user has yet not seen or not interacted with. And then on an article that came out in IEEE Spectrum not too long ago, we see, driven by computer algorithms, recommenders help consumers by selecting products they will probably like and might buy based on a bunch of things: browsing, searches, purchases, preferences. So I would say that this last definition is perhaps the widest one, the one that casts the widest net, and it's the most general one. What we're going to focus on is mostly on a ratings-based concept. And for that, we're going to need to introduce some notation. Don't be scared about the formulas. There's only a few of them, and we'll go straight to code as soon as we can to translate that into very simple Python. So we're going to need some notation. We're going to refer to U, uppercase U, as a set of users in our domain, and we'll use the vertical bars to talk about the size, the number of users that we have in our domain. I will be the set of items, and in the same way, the vertical bars around it will denote the size. We'll use we'll use I of U as the set of items that a user has rated, so either interacted with or purchased in the more general sense, but rated in the context of movie recommendations, which is what we're going to be dealing with today. And we'll use the minus notation to denote the complement of that. So in the case of I of U, minus I of U will be the set of items that have not been yet seen by user U or rated by user U. U of I will be the set of users that have rated an item, and minus U of I will be analogous to what we talked about before. So with this minimal notation, and with S being a function that talks about a notion of utility or preference, we can say that the goal of a recommendation system is to, given a set of items that a user has not yet seen, how can we distill from that the best one or the top K based on some utility measure or some preference measure to recommend those to a user? Okay, so new items that a user hasn't seen, how do we select from that pool and put them in front of the user? So with this notation and this goal in mind, really, like in many other cases of computer science, the problem of recommendations is very simple to state, at least. You can state it in one sentence with the aid of this little matrix that we have there in plain text. So in its most basic form, given a matrix of users arranged along the rows and items arranged along the columns, like this one, where I'm using U for users and M for items, think of this matrix as, for each cell, holding a rating that a user has given to a particular movie. So for example, here you see that user 3, let's think of 3 as a unique identifier for a user. User 3 rated movie 1 with 3 stars, and we're referring to a 1 to 5 rating system, okay? And then you see that there's a bunch of question marks there, because for the most part, people haven't seen all movies, or all movies haven't been seen by everybody, let alone rated, right? So this matrix is incredibly sparse. So given this partially filled matrix of ratings, which has that size, U along the rows and I along the columns, estimate the missing values. That's it. That's the recommendation problem, at least in the ratings context. Okay? Very simple to state. Are there any questions about that? Does that make sense? So there's a lot of families or ways of grouping or classifying recommendation algorithms. I would say that the biggest divide is between content-based algorithms or content-based filtering and collaborative-based filtering or collaborative filtering alone. So in their most basic form, and referring again to this ratings-only context, content-based filtering tries to estimate ratings for a user based on the history of what the user has seen. Okay, so if you're talking about movies, based on the other movies that a user has seen, let's estimate what we think is going to be the rating for a new movie. So if you think about that, a very simple way to express that would be to say, well, let's grab every item that the user has interacted with before and aggregate the ratings that the user has given to those items. And aggregation here could be something just as simple as a mean. And then let's call that the estimated rating. So if you go back to the matrix here, you could think of that as being some sort of a row-based approach, in the sense that for user U, if you wanted to estimate all the question marks in that row, then what you would do is you only look at the cells that are not question marks in the same row, and use those in some way to estimate the missing values. So Counterpart to that, or analogous to that, collaborative filtering will try to look at the ratings by other users of the same item to estimate the rating for the user in question. So if you look at the notation here, it's only just flipping around the primes. All we're doing is we're saying if we want to estimate the rating for with respect to a user for an item, then let's look at what other people thought about the same item and aggregate those opinions or those ratings and use that as a way to estimate. So if you think about that, you could imagine that being a bit of a column-based approach, in the sense that if I wanted to estimate the missing values for this column for movie 5, then I would only look at everything else that is not a question mark in the same column and aggregate that to estimate the missing values. Okay? And perhaps the word content-based and collaborative doesn't make any sense at this moment when you're looking at it in the context of this matrix. Hopefully later on, when we talk about more elaborate versions of that, those terms bear some meaning. Yes, question?
The mean in that example in that column, which is the 3, right?
So, in which column are you talking about? Yes, so the question was, if you use the mean there, it gives you a 3, which is higher than everything else. So the question was, if you use a column-based approach or a collaborative filtering approach, in the case of M5 here, you get a mean of 3 or whatever. Whether what I was going to say is that regardless of what the output is, what we're saying here about the techniques is how they operate. We're not really saying whether they are good or not. We'll talk about performance and how to measure that later down the tutorial, okay? All right. Now, the third family, which is kind of a natural evolution from the previous two, are hybrid solutions. If you look at the literature, you see a lot of examples for that. You could go about building a hybrid solution by combining predictions, maybe a voting system. You could have a content-based technique and then have a bunch of collaborative approaches incorporated into that, or the other way around. There are some papers that talk about a unifying model. I'm just going to leave hybrid solutions at that, and we'll talk a little bit more about them toward the end, but it'll be something for you to explore on your own. So, like we said before, expressing the problem is very simple. We did it in a single sentence, and I hope that it was clear for everybody. However, solving that problem is a different story. It's not a one-sentence deal. And part of that, and part of the reason for why that is complicated has to do with these challenges that we're listing here. So, in the context of a content-based technique, you're always going to be limited by the amount of metadata that you have to describe your users and your items. When you're thinking content-based, what you want to do is you want to build profiles for your users based on their taste. And if you're thinking movies, then maybe you're thinking about descriptors for genres, you're thinking about descriptors for the cast of characters, the director, things like that. If you're thinking, for example, grocery items, you want to have good nutritional information, ingredients, brands, descriptions, country of origin, things like that. Having a database that is clean with all of that data in a real-world setting is always complicated and is usually wishful thinking. It's usually something that doesn't happen. So the availability of item metadata is a problem. And then the new user and the new item problem, if you think about someone that just joined a community, or if you just joined Netflix, Netflix doesn't know anything about you. How can they recommend movies to you, right? And in the same way, a new movie comes out, nobody has seen it, we don't have any initial reactions to it, how can we recommend it to anybody? These two problems are just a way of expressing the two sides of what we're labeling here as data sparsity. If you go back to this matrix that you have up here, you can see that most of the values, by a large part, most of the values are missing. So data sparsity, getting a critical mass of ratings, is a huge challenge, and how to go about that is part of what comes into a recipe for a good recommendation engine. So, are there any questions about that, about the introduction to the problem? Yes. Oh yeah, so the question is, in the function that we're that we're defining the goal of a recommendation system, how do we describe the function S? S is just a utility function, some preference measure, some way to measure the appeal between the item and the user. Okay. So hopefully from the title of the tutorial, it is clear what this is and what this is not. We're going to provide you with a hands-on overview of a couple of the libraries, main libraries for scientific and data analysis in Python. We're mentioning IPython here because that's what we're using as an interactive tool, but we're mainly going to be focused on NumPy and Pandas, and we assume that you have zero experience with those two. There's a bonus section, like we said before, about PyTables. And of course, this is not going to be a bunch of recipes to win you the next Kaggle or Netflix, and it won't be an exhaustive review of the recommendation literature, which we hope is obvious. And this is kind of what we're going to do. We're going to first focus on NumPy, the basics, mainly the ND array, then data frames in Pandas, and then we're going to iterate over 3 versions of a minimal reco engine, and towards the end we're going to have a mini challenge, okay? And we'll talk more about the mini challenge and what it really means to do that in this context, which will just be a learning experience. We're going to use the data set by Group Lens Research, Movie Lens data set. It contains about 1 million ratings. We're going to subset that, and we'll show you how to load that. So first of all, I'll switch over to the questions notebook, show you how to load the data to make sure that everybody can load the data and have that in their namespace. And then we'll have Amr come up and talk about the big picture of where you would fit a recommendation engine in a larger system, okay? So, moving past the systems check here, in your questions handout, there's 2 cells that you will see to load the Movie Lens data. You should be able to execute this, and once you execute these commands, you will end up with 4 objects in your namespace. Those 4 objects are going to be, or 4 that matter, I should say. The 4 objects that matter are the user's data frame, the movie's data frame, and then there's going to be a movie lens underscore train and a movie lens underscore test data frame. If you load the data in this way, which is the same as you have in your questions handout, and you print out movie lens underscore train and test, you should see something that looks like that. And we'll explain what that means later. Don't worry about that, the output. So are there any problems loading the data, or is that working for everybody? Any questions about that? All right. That's great. Yeah, go ahead.
Okay, so Diego has talked a lot of theory and equations and charts, but how to put a human context into this. And we use this very, very simple use case to explain the recommendation engine problem and how it fits into the big picture. Now, I highlight that this is a very simple scenario. It can be far more complicated than this, but for the sake of this tutorial, we're going to keep it a little bit simple. So let's say you, as a user of your retailer's favorite app, you open up the app one day, there's a new cereal that you've never seen before, and you open up the product page for that cereal on the app. What happens? So the client will make a request to the API to get the details for that cereal, and the API is going to fetch that data from the database, and it's going to return it back to the API. What is that data? It's just metadata about the product. It's going to be the name of the product, an image, nutritional info if you've got it, ingredients, description, etc. And the next step is to return a score for that cereal for you. And how does that happen? Well, we already mentioned that the recommendation engine has an API layer, and so it receives a request from the client, from the web API, I'll call it, to say, give me a score for user X and product A. Now, at this point, there's a couple of things that can happen. either the recommendation engine will calculate the score in real time on the fly, if you have really robust system and lots of metadata, or what it will do is it will actually fetch the score from a pre-computed script that has run overnight and saved into a table. Once that has been fetched or calculated, returned back to the API, and then furthermore, it will be, returned back to the client as a score, either 4 out of 5, 3 stars, whatever. So that's the basic use case scenario that we're working with day to day with the recommendation problem.
Thank you so much. All right. Okay, so we're ready to get started with, yes, was there a question?
Yeah, if there are questions, let us know. We'll throw them in.
Okay. So we're ready to get started with the first library that we're going to be working with. NumPy stands for Numerical Python. And this snippet here is taken from their website. What is NumPy? Well, mainly it's a library that provides a multidimensional array object and various derived objects, but also a bunch of routines for linear algebra, for fast Fourier transforms, for random simulation, statistical computation, and many more. But mainly the centerpiece is a multidimensional array object. And you could think of these multidimensional array objects as the building blocks of everything else around the Python scientific community. So ignore what's happening in this cell here. We're just setting a few print options to make things look nice. The basic data structure for NumPy, which is the ND array, can be built using the array function there by passing in a list of numbers, for example. So what I'm using here is the convention to import NumPy, which is using the shorthand NP. And then you could build an array using the array function, which is at the top level namespace of NumPy. And you can pass an iterable, but in this case we're passing a standard Python list of numbers. And you just get back something that looks like that, okay? There are several creation functions used to populate new arrays. You can use the array function as we used before. There's asArray, there's the arange, which is an array version of the range function built into the standard library. There's ones, there's zeros and empty, and you'll also see that throughout this tutorial we're going to invoke a few functions from the random module, such as rand_n, for example, and others. So here are a few examples. All of these are top-level functions. You could, for example, execute np.zeros, and you would pass a length of the array that you want to create, for in the case of a unidimensional array, and it would get back with an array of floats that looks like that. np1s will do the analogous, but with filled or pre-populated with 1 values. There's an empty function that if you call it without the print options that I have set here, will just give you whatever is in memory at the moment. So it'll just allocate an array for you, and the elements in each of the cells, if you will be whatever was there at that moment. And here's an example with the range function. You can see that the upper bound there is not included, and everything is zero-based, just like in the rest of Python. So there's two properties to be aware of in the context of NumPy arrays. Those are called dtype and shape. In the case of dtype, it is an object. In the case of shape, it is a tuple. Dtype will tell you what is the type of each of the elements in the array. Okay? An array is supposed to be a container for homogeneous data, so everything in the array has the same type. And the dtype property is an object that simply specifies what type the data is. There's many options for that. There's float 64, integer 32, there's string, there's Unicode, there's quite a few. When you go to the NumPy website and read the documentation, you'll find out more about that. So for example, here I'm creating a random array of size 5, and the dtype of that by default is float 64. And the shape you can see here is a tuple that specifies the size of each of the dimensions of the array. In this case, we're using a unidimensional array, so 5 is the size along that sole dimension. So knowing about shape and type, you can be explicit about what types you want when you first create your array. So in this example, we're calling in PMT with an explicit D type, and we're using the top level int32 identifier to say that we want that array to be of integers. And you can see that we get back something with the correct D type specified. Here's an example using NP string, for example, and 8 there simply means that that's the longest one that we passed in. And you can also convert from one format to the other. So here's how, for example, you would truncate the decimal part by passing in, when you pass in float64, you can then use the built-in function called asType from the same array that you get, and you pass in the new type that you would want that to be cast to. Are there any questions about that, about creation, or the basic idea of the NE array? So indexing and slicing works just like, for the most part, like you would expect from a Python list. If you create an array, you can index into it using integer-based indices, and you can also use slices. So slices here specify the same as they specify in a Python list. They specify that you want from the first element up to the third without including the upper bound. It's the same zero-based syntax as in regular Python. And you can use the colon operator here to say that you want starting from or ending from, and the twist to that is using the minus notation, which simply starts from the end and goes back that many elements. So here's an example in which we are using the notation of slices to set 2 elements at the same time, for example. So one thing you can do is say index into the last 2 elements of the array, and you can use that as a way to, combined with the assignment operator, for example, to change the original array that we have up here to look like something what you have down there with 2 arbitrary numbers at the end. Okay? Are there any questions so far? So for multidimensional arrays, you don't need to worry about 4D, 5D, because it really gets complicated. But the basic idea is that as you index into the array, say for example you had something of this shape, you are walking along the dimensions, and in the tuple that you have, you will end up with these shapes described here. And there's a few examples that we'll go over in the questions part for this section of the tutorial to make that a little more clear. But let's give you an example. Suppose that you have a 2-dimensional array, which is basically a matrix, and it looks like that. If you simply pass a single index as an integer into the indexing method, what you get is a row. Okay, so you're indexing into the first dimension there. And if you wanted to get, for example, the first column, you would use the colon operator to say, I want all rows of the first column, 0 being the first column. One thing to notice here is that notice how NumPy doesn't have a notion of a column vector. For those of you that work with matrices or perhaps MATLAB, there isn't a notion of a column vector. So you see that here the shapes, in the case of a row portion of this matrix, has 3 elements. And in the case of a column, it has 4, but there's no way for us to know whether that was a row or a column. Okay, so you have to keep track of that yourself. One thing to mention is that when you're doing indexing in this way, you have to be careful because what you get back is a view, and that means that basically you're not getting a copy of that sub-portion of the array. So to illustrate that, if you have an array and you get a slice from that, and then, for example, you modify that slice, really the slice behaves in the same way as any other NumPy array. So if you modify the slice, you have to be careful because you're modifying the original array as well. And this is something that is built into NumPy to avoid quickly consuming up all of your memory. Fancy indexing has, depending on where you look at and where you read about it, it's been referred to as the ability to index with either Boolean indices or with list of locations. Sometimes people refer to list of locations only as fancy, and this has its own name, which is Boolean, but we have fancy there just so that depending on where you read about it, you can identify it. The idea of Boolean indexing says that using true-false elements in the array, you can, in that way, select the portion of the data that you're interested in. So in this case, I'm creating an array of d-type Boolean, and by using that as an index into this simple array of two integers, we can index into it and say that we only want, for example, the first value. Now, the more interesting example of this comes when you use the Boolean operators or conditional operators to learn something about the properties of the data that you have inside an array. So for example, if you have an array of random floats here of this size, you could ask which ones of those are less than 0, which ones of those are negative, and what you get back is an array of d-type Boolean telling you in which indices that condition holds. Now, that is quite useful, but it is even more useful when you can grab this whole thing and put it inside the square bracket notation for the indexing method, and use that as a way to extract the portion of the data that you're interested in. You can use more elaborate conditions, such as that one. You can ask about a range, for example. And you can also use that as a way to set elements in the array. Now, I should mention that as opposed to indexing like we talked about before, simple indexing, this will return a copy of the array. So it won't be a view. But you can also use this as a way to assign values. So this is a way of saying, for example, set everything to 0 wherever you have a negative value. And you see how expressive and simple that is. Now, list of locations is perhaps a bit more complicated, and we probably don't need to spend too much time on it. But the idea is that if you have a matrix like this one, you can pass in a list of integers to say, for example, in this case, which rows you would like to select from the matrix. And if you repeat, you will just get the rows repeated. So in this case, we're saying I would like the first row, and then for here, see how the second to last row is repeated here. Okay. The more general version of that is passing in two lists to the indexing method, and what you get basically is something that says, this is the list of locations approach. I would like the element in row 5, column 2, row 3, column 1, row 1, column 0, and that's why you get 3 elements there. For those of you that are more familiar with MATLAB, perhaps you would have expected a square or a subsquare of the matrix, and there's a way to do that using the IX method. So I won't spend too much time on that because it won't be critical to this tutorial. So having said that, what we're going to do is go to the first question set. So switch over to your questions PDF. And what you will see there for the NumPy section is something that looks like this. There's a first set of 1, 2, 3, 4 questions. So we're going to give you a few minutes to go through those and actually solve them. You can grab us if you have any doubts about how to proceed, and then we'll keep going.
So we're just running a little bit behind, but I think it's okay because the break is at 10:50. It's a little bit later than we had. So that's fine. I think it will get us right to campus. So I need to speed it up a bit. How far behind are we? I'd say about 25 minutes. Well, yeah, because I have to go 7 Yeah, it's okay. Yeah. And then another thing next year is we have to put a virtual link in those units with 6. We should have done that. I don't know why we didn't think of that.
No one else can ask me a question.
There was a question about the export, the PDF export of the questions notebook. Part of the output is cut off for some of the arrays. When we're doing these examples for indexing, so for example, I think it was this example because it's really wide here. It doesn't really matter what numbers you work with. You can make up an array of your own if you want using that function, and you'll learn a little bit about array creation at the same time. But the goal of this exercise is to use the concepts of Boolean indexing. So it doesn't really matter if the numbers don't match exactly. So I think there was a problem with the doing the PDF export and getting the print out of that. Okay. Okay. I'm wondering why. Okay. So since that part is we're still at the early stages of the concepts that we want to get across, we're going to move hopefully a little bit faster in this first part so that we get to the core of pandas, which is really where we want to be at. Okay. So moving along with NumPy, there's two more concepts that we need to look at. Those are vectorization and the broadcasting rules. Really, vectorization is a simple idea, and it is just saying that the way that NumPy is built is so that you can take advantage of the simplistic syntax and use, for example, the operators that you're already familiar with, but with arrays. So in this case, what you get, for example, if you have an array with these numbers and you say array minus array, what you get implicitly is an element-wise result. So the result would be an element-by-element operation, and in the same way, if you use the star syntax, what you get effectively is just a square of each of the numbers. More complicated it can get a little more complicated with the broadcasting rules. So whenever you're doing vectorized operations between arrays, there is a set of rules that apply to make sure that the shapes are compatible to operate between two arrays. And those are known as the broadcasting rules. So those work very simply when you're looking at, for example, operations between a scalar and an array. So here we're saying, for example, 5 times the array is just an element-wise operation between 5 and each of the elements of the array. So you could think of 5 as being broadcasted along that dimension of the array, which is why it's called like that. And in the same way, this works if you're adding a scalar, or for example, if you're raising each of the numbers to a specific power, which would be in this case equivalent to getting the square root of each of the elements. So if, for example, we're going to go through an example that is a bit more involved, I'll go fast through it. You don't have to worry about the details if they don't make sense, because this won't be essential to the parts that we're going to cover later on. But say, for example, that you had a matrix of random floats that looks like that, and you wanted to obtain the mean, where I'm using the mean function at the top level of the NumPy namespace. with an axis of 0 to obtain the mean row of that array, what I would get is an array of 2 elements, each one being the mean of the columns of the original array. And I could do an operation like that, which would broadcast the smaller array across the rows of the larger array. And it would give me something that I'm calling that to be the centered rows version of the array. So of course, when I do a mean on the centered rows with the same axis, I'm going to get 0 because I've already demeaned everything along that axis. But if I were to do the same thing along the columns by passing an axis of 1, what I would get is an array of, in this case, 4 elements, each one having the mean of each of the rows. So this operation no longer works because the broadcasting rules don't apply. So one way to get around that is by reshaping that into something that is a bit of an artificial column vector that you can then pass into the same operation that we were doing before, and that would work. So really the gist of that of this example here is that whenever you're working with 2 arrays of different shapes, you have to be aware of how the operation between the 2 is going to go about. And for higher dimensions, this can get really complicated, and sometimes you need to draw pictures and things like that to know what's going on. I want to mention a note about NANs. Given the standard that NumPy follows for floating point, NAN is by definition different from everything else. So when you apply that definition to NAN itself, what you get is something that looks like that. NAN is not equal to itself, which can be a little counterintuitive. And the reason why we're saying this is not just because it's an oddity, but because if you wanted to identify missing values or NANs in an array, you wouldn't be able to do it with a standard operator such as equals, right? Because by definition, that's always going to be all false for everything. So there is a built-in function in NumPy called isNAN that you can use to identify the NAN values, okay? So having said that, let's go to the second and final question set for NumPy to explore those concepts a little bit, and then we'll keep going with pandas. So there's only 3 questions for this set. Okay, so for this question set, there was a bit of a trick because we didn't really talk about operations, and we're asking you to compute sums and means. And we're doing that on purpose, and the reason we're doing that is so that you know that there's 2 ways of expressing, as far as the syntax is concerned, these basic operations. You could, for example, do something like this using the top-level npSum function, or you could even use the standard library sum function, and obtain the sum of the array, okay? And in the same way, NumPy arrays have built-ins as methods of those objects that allow you to do these basic operations as well. So this, for example, would return the same thing. And we want you to get familiar with both ways of doing that. This also holds for this second exercise about the mean, for example. You could say array.mean, or you could say npmean of the array. There's 2 ways of computing that. We also want you to be aware of these 2 ways of expressing these operations, because when we get to pandas, sometimes pandas will override those operations with respect to what you would get in NumPy. And it's important to be aware of the differences, especially when it comes to the handling of missing values or NANs. Okay? All right. Were there any questions about that? Okay, so we're ready to get started with pandas. This is where we're going to spend most of our time, and most of the more complicated Reco engine exercises are going to be using the power of pandas. So pandas is a Python data analysis library in the same way that we did with NumPy. This is extracted from their website. For those of you familiar with R provides a data.frame object, and the creator of pandas wanted to have something like that, but more powerful in Python, and I think that this library is just amazing for doing many things. It features a powerful index object and built-in data alignment and the handling of missing data. And then we're going to get into some of the very cool group by and aggregation capabilities that are available in pandas. So in the same way that we did with Python, with NumPy, please ignore this first cell here where we're setting just a few print options, and we're going to go through the two most basic data structures in pandas. One of them is the series, and the other one is the data frame. Excuse me. And here you can see that there is also a convention and a shorthand notation for importing pandas, and we're using the convention PD. And we're going to get started with the series. Now that you're familiar with NumPy arrays, understanding a series is going to be quite simple. If you already have a NumPy array, one that you're already familiar with, such as this one that we'll call values, you can construct a series by using the most simple form of the constructor, which is to just pass in, for example, a list of numbers or a NumPy array in this case. If you print that out, what you get is an indexed array or an indexed version of the same array with an index that is automatically built for you. And this is kind of starting to look like the dictionary for those of you that are familiar with the dictionary. And that's because the series is dictionary-like as well. The more, a bit more expressive way of initiating an array is by not only passing values, but also passing perhaps more meaningful indices. And so if you have a list of labels, such as A, B, C, D, all the way through H, for example, in this case, and you instantiate a series with the same values, then you get the exact same thing as before, but your labels are now perhaps more meaningful. And the most expressive version of them all is having an arbitrary Python dictionary, such as a movie rating instance that we call here, that specifies numbers, it specifies strings, for example, and you could pass that into a series constructor, and now you would get an indexed NumPy array with the labels that you had in the original dictionary as keys. So there's two properties, clearly from what we've been talking about, there's two properties that you need to know about the series, and one of them is the index, which is a pandas index object, and the other one is the values, which is just the values that are contained in the series. So very analogous to a dictionary. You can index using integer-based indices, like in this example, series you're indexing with a 0. Or you can also index using the perhaps more meaningful label-based indexing, for example. And there is a built-in get value, which the pandas creator suggests to use when you know that you just want to get a single value out of the series, given the overrides of the other accessor methods, which make this a bit faster. Now, what is the power behind this if we haven't really seen anything beyond something that looks like a dictionary? The operations between series with different indices are handled automatically as far as data alignment is concerned, which makes sense, is very intuitive, but in fact is very powerful. So for example, look here, we have two series, each one with 3 values, but with different indices. The only indices that overlap between the two are A and C. So that means that in the result, whenever we add these two, B and G are going to have NaNs because they're being added against something that doesn't exist in the other side. Okay? The data frame is the other object very important in the pandas library that we're going to look at. And you could think of this as a spreadsheet, really. I think that this is the best analogy when you think about a data frame. So think of it as a spreadsheet whose columns or rows are series objects. You can instantiate or build a new data frame with a dictionary of equal length lists, for example. And here I'm passing in a label for the columns. So see how by saying column 1 is a list of numbers and column 2 is another list of numbers, we get a spreadsheet with the labels there. That's the print format that we have. That's the wrapper for the notebook. So maybe if you're working in your local shell, it won't look exactly like that. And you can explicitly, in the same way that you can explicitly set index values in your series, you can explicitly set column values in your data frame. And you can use the most expressive constructor way, which is by passing in the args for data, for columns, and for the index. And now you have a fully specified spreadsheet. So you can think of it as a dictionary of series objects as well. If you have, for example, these 2 movie ratings, and you created a data frame with the first rating and the second one as columns of that, this is what you would obtain. And notice here that we're naming the columns and the index with the name, accessing the name property, just so that we get something meaningful here when we print it out. There's a built-in T method, which is the same built-in T method that you will see in NumPy arrays, to transpose, which will interchange the columns for the rows. And naturally, the data frame will have these 3 properties: columns, index, and values. Columns and index being of the same type, and the values just being a NumPy array. In this case, since it's mixed type, the D type is object. Okay? You can add and delete entries from a data frame by using the drop method. You could, for example, get rid of a row in this way. You could get rid of the genres row by passing in an axis of 0. And you could drop a column by passing in an axis of 1. And you could even add a new column by using dictionary notation in this way. But you have to be careful that the order of things that you pass in your list is correct. Okay? So having presented the basics of series and of data frames, let's go to the question set for pandas, which I believe has, let's see, 1, 2, 3 questions. Only 3 questions for the first set for pandas. Yes?
To get that thing to drop, I had to assign the drop to something else. DF2 DF drop.
Okay, so it's good that you mentioned that. Thank you for that. So the question was regarding the drop method whenever you want to delete either a row or a column. So I should mention that here, for example, whenever we're calling the drop methods, what we get are new objects. So if you wanted DF, if you wanted to see a change reflected in DF, you would have to reassign it, for example, which is what happened there. So thank you for that. It is a copy. It is a different object, right? It's a different object with a different index. Okay, so in the interest of moving a little faster through this first part, let me get into data frame indexing, which is really something that you are going to need for the more advanced exercises, especially when we get to the reco engine part. You can index into a column by using its label. So this is the dictionary notation, for example. You could say df and the square brackets for a label of a column, as you can see over here. Or you could use the dot notation, which works the same way. And in a more complicated manner, you can pass in a list, for example, of labels to index into a subset of the columns of your spreadsheet. Now, the more expressive way of indexing, both in terms of cross-section and column-wise, is by using the IX method, which can take, for example, in this case, a row identifier, which is, we're using observation numbers for the rows, and it'll give you a cross-section indexed by column, right? So what you're doing there is you're taking a row of your spreadsheet, of your data frame, and then you're going to have a different value for each of the columns. And you can also use integer-based indexing if you wanted to index according to a particular order, for example, the first row in this case. The IX method will also take what you already know from NumPy, which is slices, and the column notation, and you can be more expressive by passing in both row and column identifiers. And so in this case, for example, we're saying we want the first 2 rows, but only for column 2 of the data frame. So knowing the basics of the IX method, so I should mention that in the last case here, for example, we're doing the same thing, but for a subset of the columns. So you can combine everything that we talked about before into the more expressive ways of indexing using the IX method. So for that, for indexing, we have a dedicated portion of the question set. Indexing is going to be very critical for what we're going to do later in the recommendation engine section. And if you switch over to the question set for Pandas indexing, you will see that this is the first time that we're dealing with the data set. So hopefully you already have MovieLens train and MovieLens test loaded into your namespace. So what we're asking you there is to play around with those 2 data sets and to learn use some of the indexing methods that you learned from before. So we'll give a few minutes for that. Can everyone hear me okay? All right, cool. So welcome back. We're going to start the second half of the tutorial. First of all, I want to make sure that I know Amber and Zach have both been going around the room. I want to know if there were any questions about what we talked about before. The ND array, series, data frames, how those two estimate functions for collaborative and for content-based work. Did everybody get a chance to play around with the training set and all of that? All right, cool. Okay, so to get started with the second part, we have more formulas. So what we're going to try to do is to generalize the notion of the aggregate function that we talked about in the beginning. So in the beginning we talked about content-based systems and collaborative-based systems, and in both cases we had an aggregate function which we said could be just a simple mean. So in the case of content-based, we're looking at a single row of the ratings matrix, and we're aggregating those ratings, the ones that are not question marks, we're aggregating those using something like a simple mean. And when we're talking about a collaborative system, we said that was kind of like a column-based approach, and we were taking every rating in there that wasn't a question mark or that wasn't missing, and we were aggregating that in a very simple way, again using a mean, for example. So how can we get fancier or more sophisticated for both of these cases? Well, the first thing that we can look at, the first thing that we can tweak is the aggregation function and make it something more, perhaps more meaningful than just the simple means of the rating. So in the context of content-based, what we can do to generalize the aggregation function is perhaps possibly incorporating data, metadata about the items. What we can do is, instead of computing a simple mean, which is a mean of uniformly weighted values, what we can do is compute a weighted average with weights having some sort of semantics that depend on whether we are looking at a content-based or a collaborative system. So for content-based, we could do a weighted mean based on the similarity between the item that we're trying to estimate the rating for and all of the other items that the user has seen and has rated, right? So say that there's a new movie that we want to estimate a rating for a particular user. And so we look at everything else that this user has rated or has seen, and rated because we're going to need the rating in this case. We'll look at everything else that the user has rated, and we see how similar those movies are between each other, and we use that as a weight for the average. So maybe they shared somebody in the cast of somebody in the actors, or maybe they had the same director, or something about the soundtrack, if that's perhaps is meaningful to the user. Whatever that might be is what we're trying to represent with the sim function between two items. So a more elaborate case of that would be to, instead of looking at a simple weighted average, is first of all, let's take into account perhaps whether this user is a very critical user, or he's someone that is more forgiving when rating movies. You see someone that is really harsh and tends to rate things 1 or 2, or you see someone that rates movies really highly. So perhaps it's more meaningful to look at the distance between that mean rating and the rating that he or she gave to the other items, and then weight it accordingly to the similarity function. So k in this context is just a normalizing factor. You can ignore that. NumPy will take care of that for us when we use NP average as well. I believe so. And then we're using the bar notation for average rating. Notice how the collaborative filtering case is just the same. We can generalize in the same way, except that we're switching I's for U's. So now the similarity function becomes a similarity function between two users. So hopefully at this point, and this is what I meant at the beginning when I said the word collaborative and content started to make sense, hopefully at this point you get a feel for why content-based is called content-based, because you're looking, when you want to compute a similarity function between two items, you have to look at what the item is and represent it in some sort of mathematical way, in some sort of vector. So in order to do that, you look at the content, and that makes your recommendation engine, which perhaps is a drawback of content-based system, it makes it vertical specific or domain specific, right? Because you're looking at the descriptors for the items in your domain. in the case of collaborative filtering, when you want to do a similarity between two users, you could have a user represented by a profile. And a profile could, again, be a vector of features, and it could also be a content-based profile, but it could also be that you're just comparing users based on their rating history, which makes your entire system vertical or domain agnostic. And we're going to look at some examples of that. So I think that from now on, after we pass aggregation in pandas and we look at the RecoEngine version 1.1 and 1.2, we're going to mostly focus on this version of collaborative filtering, and we're going to try to generalize the aggregation function, but only looking at the history of ratings. Even though we can apply the functions to something else, we're only going to look at the history of ratings when trying to compare two users, okay? But hopefully at this point, you can get a feel for however many ways you can mix and match techniques to build a RecoEngine, okay? All right, so let's talk about aggregation in Panda. So we said that we were going to try to generalize the aggregation function. Well, Pandas has a built-in aggregation kernel or set of aggregation functions. And it's all around two functions, I should say, group by and pivot table. I think there could be others, but I think those are the only ones that we're going to look at. And it's all around the idea of split, apply, combine. If you're familiar with MapReduce, it kind of resonates with that. But the idea is you split your data in your object according to a key, and you group like that, and you apply a function to each of the subsets individually, and then you combine everything together into a new object. So let's translate that into an example with movie lens train. And let's say that we wanted to get the mean rating by gender, right? So that's a very simple notion. We want to know what the mean rating is for males and for females. And we can do that with this simple one-liner. So we say group by gender, and the subset of the data that we want to aggregate is going to be ratings, right? It's of numerical type, so it makes sense to aggregate it using a mean, and that's how we specify that. We could also group by and aggregate using multiple keys. And so, for example, if we wanted to group by gender and age and then compute the mean ratings, we would just pass in a list of the two identifiers, and we would get a result which, as you can see here, is a data frame with a hierarchical index. We didn't really talk about hierarchical indices. It's an entire topic of Pandas, so I suggest that you take a look at it, but the basic idea is that one, and that is that you can index into a data frame with something that is of multiple keys. So in this case, it would be the gender first, and then an age identifier. So Movie Lens splits the age identifier into these values that you see here, which probably means in between or less than or equal to, something like that, okay? So the other method that I talked about for group by is called pivot table. The notion of pivoting in Pandas is a bit more general. The idea is that you can get a square, you can arrange your spreadsheet into a square of rows and columns according to the IDs that you pass to pivot table. So let's start with an example that has nothing to do with aggregation, okay? We started out the RecoEngine talk by saying that usually what you get is a matrix of ratings, and you have users arranged along the rows, and you have items arranged, or movies in this case, along the columns. So one way to extract that or to build that ratings matrix from the spreadsheet that we have from Movie Lens is by using pivot table and saying that we want the body of the table to be the rating values, and the rows are the user IDs, and the columns the movie IDs. And in this case, there's a single rating per user ID, per movie ID, so there's nothing to aggregate, really. All we're doing is we're just rearranging our data into this square, if you will. And once we have a ratings matrix, which is also a data frame, I'm showing here how to use the IX method to look at a subset of that. Imagine a subsquare of that huge matrix. We're using a subsquare of that, and we're moving it around, and I'm just randomly or arbitrarily choosing to look at a 15 by 15 subsample of that. So this just gives you an idea of what a real ratings matrix would look like, and we are also showcasing how sparse this is, because most of the values are NANs. In fact, in this particular 15 by 15 subsample, everything is NaN except for that one value over there, 2. So the more interesting case of pivot table is when you use it as an interface to group by. So this is why we're talking about pivot table in the context of the aggregation framework. You could take the example that we talked about before, except that instead of doing by gender and age, we're doing by gender and title, and we're computing a mean. So we get a similar kind of thing to what we got before with the hierarchical index, and this is saying that for each gender and title, here is the mean rating. So one way to make that look perhaps a bit more readable is to get rid of the hierarchical index and put it as another column. And you can do that using unstack, right? So don't worry about this complicated one line here, but I'm just adding some more things after the group by. And after the mean, I'm unstacking the gender, which results in a table that looks like this. So this is saying on a per title basis, I want to know the average rating, both for male and for female, for that movie. And so one way to more easily express everything that you see up here, which is this long one line, is by using pivot table as an interface to group by. So you can use pivot table by specifying values of ratings, rows of titles, and columns of gender. And by default, the aggregation function is going to be a mean. You can specify it if you want, but by default, the aggregation function is going to be a mean. So you can see that the result that we get is exactly the same. You can check, in fact, the values are the same because we're looking at the first 10. So it is exactly the same result, but we're using syntactic sugar to obtain that. Are there any questions about that? Yes, it's just like a Unix head command or a tail command. There's also a tail command. Yes. The top 10. Yeah, the first 10. So maybe in the case of the movie lens train data set, this kind of solves the problem of the label indexing that we talked about before, because you could just get the first row using head. Yeah, good point. All right, so minimal reco engine version 1.1. Using the pandas aggregation framework, we can now try to implement some of the more advanced aggregation functions that we talked about before in an implicit way. And the reason why I say implicit way is because we're not going to build those sim functions that we were referring to before just now. We will in a later version. But what we can do for now is try to see how this framework helps us to build a reco engine that is slightly more sophisticated. And you will see here that sophisticated isn't always a synonym for better performance, okay? So you'll see some results right now. So the first thing I'm going to do is take the users portion of the data set. So from the original data set that we loaded at the beginning, I'm going to take the users data frame, and I'm going to use the set index on user ID just so that we can access user information a bit more easily. You'll see why later. But basically the idea is that with this data frame, I can now say, for example, for this user ID, I want to know the gender, and it's an easy way to get that. So let's take a look at collaborative-based filtering using an implicit similarity function. So here in estimate 3, what we're doing is we are trying to estimate ratings using the column-based approach, so a collaborative filter, but we are only going to consider those movies that were rated by other users, or I should say, we're only going to consider the ratings by other users that are of the same gender as the user for which we want to estimate. Does that make sense? So I'll repeat that. So we're looking at a collaborative-based approach. So that means that if we want to estimate a rating for a user, we're going to look at other users that have rated the same item. Now, using an implicit similarity function, what we could do is say, well, my similarity function is going to be a very simple one. If the other user is of the same gender as I am, output a 1. If the other user is of a different gender than I am, output a 0. So that effectively translates into ignoring everybody that is of a different gender when looking at all the other ratings by other people for the same movie. So we can do that using the pandas aggregation framework. I'm computing means by gender here, which is the exact same data frame that we had up here. The only difference is that instead of having titles, we're having movie IDs, just so that we can index on that. And then using that means by gender and the user info data frame that we built up here, I'm just going to return the mean, right? I'm just going to return the mean for that movie ID and people of the same gender. Okay? Are there any questions about that? Does that make sense? So regardless of whether that's a good idea or a bad idea, maybe our RMSE went up, I don't know, but does that make sense? Right? So that's one way of using the aggregation framework, and we're implicitly specifying a similarity function between users. So at this point, I think it's worthwhile to mention that when we're doing this on the fly, it's perhaps not the best idea to be calling the pivot table every time a request comes in to estimate 3. So going back to the reco flow that Amer talked about in that picture, sometimes it makes sense, like in this case, I've actually timed this, and you can time it yourself as well to verify. Sometimes it makes sense to split up the work that is done by the reco engine into a learning part and an estimation part, kind of like you see in machine learning in general. So in this case, the learning part, something that is kind of done offline, will be computing this means by gender data frame so that we have it readily available whenever we want to estimate. So now our minimal reco engine has kind of evolved into this mini class that has a learn method and has an estimate method. So the learn method will just compute the means by gender using the pivot table. It's just a one-liner. And then we're accessing that whenever a request comes in. So for the same reasons that we talked about in terms of how we split the data, we need to make sure that the movie ID is in that data frame. Otherwise, we fall back to some methodology. Maybe you can come up with better ideas of how to fall back as opposed to just returning a 3. And then after that, we get the gender for the user in question, for the user that we're receiving the request for. And we're making sure that there are, from the other people that have rated this movie, we make sure that there are other people of the same gender as me or as the user in question, right? Does that make sense? So that's why we're using the isNaN function there. Otherwise, we will be returning an NaN. So here we have like 2 edge cases to consider. First of all is make sure that other people have seen this movie, number 1. And second of all, that there's other people of the same gender that have seen this movie. If there aren't, in the first case, we fall back to a default 3. And in the second case, if there are no other people of the same gender, then we default, or we fall back to a default of the same type of collaborative filtering that we presented at the beginning, which is just aggregating over every gender, regardless of males or females. Okay? Yes, question?
So, gender is a pretty straightforward field in our data frame over here.
Yes?
However, if you computed fields, say for example, only collaborate by rating with people who have rated for more than 3 movies.
Okay, well, great. We're going to get into that. That's a very good question. So the question was, how do I incorporate more advanced notions into the similarity function? So in this case, we're only saying the people that are of the same gender as I am, and this is readily available in our data set, so it makes sense. It's easy to compute it with the pandas aggregation framework. How do we get more sophisticated with the similarity functions? Well, it turns out that in the pandas aggregation framework, you can go with the pre-baked aggregation functions that are built into the library, or you can pass in an arbitrary function of your own to compute these similarities or to aggregate. Okay? So that's what the next version of the reco engine that we're going to look at is all about. So first of all, before we go there, let's look at a similar example to reco 3. In this case, our implicit similarity function between 2 users is going to say, if we are of the same age, output a 1. If we are of a different age, output a 0. Okay? So this is our implicit similarity function. And we have the same fallback examples. And here's the RMSE. Again, I didn't say this was a good idea. And RMSE is kind of telling me there, we're not really improving the performance. Okay? Good. Yes, question, yes.
If you're doing, if you want to weight things like gender and age instead of using identity for the
value?
Yes. Yes. So if you wanted to do that, you could use the argument for the aggregation function into pivot table to specify that. But let me show you, I think that the question is kind of resonates with the previous question because it talks about how do we manipulate the aggregation function a little bit more as opposed to what we just get directly from pandas, okay? So for that, let's get into our minimal reco engine version 1.2 with custom similarity functions. So really similarity functions I think is also just like evaluation, training and testing, performance criterion. I think that similarity functions is also a little topic of its own. You want to know how your similarity function behaves. You want to know what the range of values are and what they mean. I suggest that you dig into that on your own. Here I'm just presenting a few of them, and I've written them, and we have presented them with the NumPy syntax, but we haven't really made sure that they check for weird edge cases or things like that. So I suggest that you read through them on your own offline after the tutorial. We're going to be using this one down here. So let me go through them one by one. So here's Euclidean similarity. It is similarity there because Euclidean is really a notion of distance in Euclidean space. So this is a trick just so that we get a similarity notion out of that. There's cosine similarity, Pearson correlation, which is kind of like cosine similarity once you've centered your data, each of your vectors. And then I have a Jacquard similarity and a binary version of that. So let me say that these are all written to operate on two series, on two pandas series, as opposed to two vectors. So think of a pandas series as a profile for a user in the context of collaborative filtering. So since we're talking about building a custom similarity function that compares two users, let's assume that we're going to describe each user with a feature vector. And that feature vector, we're going to represent it in Python using a series. Okay, so think about the index of that series being the name of each of the features, and then you have a value for those. Okay, so what these functions are doing is taking those two series and outputting a similarity function for them. So imagine, and actually this is what we're going to do in the next version of the reco engine. What we're going to do is we're going to say a user's profile will just be his or her history of ratings. So if you wanted to know my profile would just be a series whose index are movie IDs and whose values are ratings. Does that make sense? My rating history is my profile. So now if I take my rating history and somebody else's ratings history, then I can call this function and plug it into the arguments of one of these functions, and I would obtain a floating point value in return that tells me how similar those two ratings histories are. Okay? In the context of a Pearson correlation, this is what we're going to be using for one of the examples. It is just looking at, if you plot the data one versus the other in the ratings, it is just looking at how well can you fit a straight line through those data points. Okay? And I think that now that I remember, in particular, Pearson correlation has a very cool PNG figure in the explanation of Wikipedia that shows you the values for whenever the data looks like. Maybe I can pull that up when we're doing the exercises to show you, but that's just so that you know how it behaves. Okay? So that's the idea of Pearson correlation. It's just outputting a similarity between the two ratings histories. So now that we have that defined, we're going to write our last version, or this is the last version of the reco engine that we'll present to you, and then you're going to write a bunch of your own. So reco 5 here is looking at a very similar idea that is just the evolution of an implicit similarity function, but using something that is custom, namely that Pearson correlation function. So what we're going to do is the following. Whenever a request comes in for the reco engine to estimate a rating for a particular movie and a user ID, we're going to grab every other user that has also rated this movie. We're going to grab their profiles being their rating histories, and we're going to compare those profiles against the user in question from each of those comparisons, we're going to get a floating point value, and we'll use that to weight the averages as weights to our average to estimate the rating. And luckily, I think that this version seems to be the better performing one of all the ones that we had up until now. And that wasn't hard because we really had very basic stuff before. But hopefully this goes to show that when you're looking at how similar two users are before considering their rating, you can improve upon your results. Okay, so just to go through the code here, first of all, we're getting the ratings by others, and we're doing the same trick in case there's no ratings by others on how to fall back. We are setting an index on user ID into that data frame. And then we're looking at what are the IDs of those users, what are the ratings of those users, and then what are their profiles. So the profiles is something that is built in the learning phase, and it is just a pivoted table that looks at on the columns each user ID, and on the rows each movie ID. So basically just a ratings matrix. And so now if we index into that data frame, say for a particular user, we get back their profile directly. Right? So it's simple to use indexing once that's built. And then using indexing into the same object, we are obtaining the profile for the user in question, which I'm calling user profile. So at this point we have their profiles and we have the user profile. And now comes the interesting part, which is the apply function. And you'll see apply throughout pandas. You can use apply in the context of grouping. You can use apply in the context of a simple data frame or a series. Apply allows you to take a custom-built function and apply it along whatever dimensions or whatever aggregated group or subset of the data of a data frame or a series. So in this case, we're taking the profiles that represent the profiles for the other users, this data frame, and we're applying a function that simply says compute Pearson correlation with respect to the user that we want to estimate for, which is user ID. Okay? So I'm just passing in a lambda function. It could have been a named function or an actual def function. This is just a matter of taste, really. And so once we have the similarities already computed, we're passing those similarities over here into the NP average function, which is a new function that we haven't talked about up until this point, which is just the more general version of mean that takes weights. So see how the weights are the similarity floats between the user in question and everybody else that rated the movie. And then all we're doing is we're passing this over to the little evaluate framework that we had to see how well it performs. Okay, are there any questions about that? So take a look at how, yes, go ahead.
We had this rating scheme before that talked about gender and weights of 0 and 1.
Yes.
Now we have this, which is based on similarities. Now I say, what if I want to put those together somehow? Maybe I don't think 0 and 1 are the optimal weights, and something between 0 and 1, 80% of that, 20% of that. And I could search for that or something like that.
Yes, yes. So there's ways to do that using apply, and probably what I would do in this case is I would modify the lambda that I'm passing in here to say that whenever I'm looking at a profile by another user, I can key with that user ID into the user's data frame and obtain this extra information that you're talking about, gender, age, things like that. Really, the idea for the rest of what we have in the tutorial is that we explore all of these combinations. Just hopefully at this point you can see that when you build a reco engine, you have an exponential amount of ways in which you can combine things, not only from the basic families and how you can derive from that, but also in the ways that you can plug the holes whenever you have missing data or whenever you need to fall back when something is missing. And that gives you some hybrids there. So the purpose of the rest of the tutorial is to explore that, and we're going to do that through a mini challenge. Okay? And this is not a real challenge, so don't worry about coming up with something that performs really well or whatever. What we want to do with this challenge, and we're glad that we have so much time to do it because this is, I think, the best part of the tutorial. What we want to do with this challenge is get everybody comfortable with mixing and matching and combining the things that you can do with the built-in aggregation framework in Pandas and with custom similarity functions and all of these things. So that's the focus. And once you have something that you're kind of comfortable with, forget about the RMSE, that doesn't really matter. But once you have something that you're kind of comfortable with, you can iterate on that. And then using the evaluate function that we wrote for you, you can get a floating point value that says this is my RMSE for my minimal reco engine. And then Zach has come up with a nifty way for us to post that score into something that will look like a leaderboard up on iPydra. So before we get started, I would like to see a show of hands for people that have at least a year of Python experience and some exposure to NumPy. So keep your hands up, please, really high. Okay, so keep them up. Those of you who are not raising your hands, please take a look at those that are raising their hands, okay? Because what we would like to do is to pair you up. Okay, hopefully we can also get pairings based on whether you have, thank you for the hands, whether you have set up successfully a local environment so that everyone's not testing against iPydra. So hopefully we can pair up in that way. So we strongly suggest that you pair up and do it in groups of 2. That's the best way to learn. And once you've paired up, go to the iPydra login page and create a name for your team. Okay, whatever your team, whatever you want to call your team, something simple so that this doesn't blow up because this is not testing for weird code that you might be inputting into the text field or whatever. Yeah, alphanumerical. Thank you. Yeah.
No periods, no dashes.
Exactly. Nothing weird like that. So pick a name for your team. We expect to only see about 40 entries there since we have about 80 people and we're pairing. And that's also for the purposes of being able to have the server withstand the load. So the purpose of, so the way we're going to go about it is if you go to the questions notebook here in the mini challenge, you will see how to write the compute RMSE function, how to write the evaluate function, and then how to write what the prototype of your estimation function should look like. Whether you use a class or whether you use a standalone method is your choice. That's the signature that it should have. And this is how you could get an RMSE for your method. And once you're kind of happy with that, you can go to the hosted notebook using the login that you created for your team. And I suggest that you only go to the hosted notebook at this point so that you don't use the hosted notebook to test and to iterate because otherwise resources are just not going to hold. And once you have a function, then you can go to the hosted notebook, write it out, and there's an update score little function that will be magically there in your Python path that you can import, and you can use that to post your score to the mini leaderboard that we're going to have. Okay? So we really want to stress out that this is not a real challenge at all. And this is just so that we can get at those last 3 or 4 questions that we had, which is how do you mix and match, and what about if I wanted to pay attention to only a few of the males and a few of the females, or maybe look at other attributes in them. So that way you can, probably the first thing to do is to get familiar with the other fields. There's genres in the movies, for example. If you wanted to build a content-based, maybe we end up realizing that the way to go in this case is using a content-based filter as opposed to a collaborative-based filter. Things like that, okay? Are there any questions about that? All right, so go ahead and let's get paired up, and we'll be roaming the room to help you out. Okay? Thank you.
Survey. I need to mention the survey.
Yeah.
So can you bring up the Stuart's email? And because he has links to the survey.
Yeah.
And when you bring them up, I can just say a few words about it.
Okay. Yes. Yeah. Right. So if you go back to here, we have written from version 0 to version 1.2. We have written several versions of this estimate function. There's hundreds of others that are out there. So basically, you can start with one of those and start tweaking and looking at perhaps other ways to produce the estimation. But so for example, one way in which you could evolve or change this last reco engine function, which is reco 5, instead of using Pearson, for example, you could try using one of the other similarity functions. Maybe Euclidean at the top, right? And you would change that. So the estimation function is always going to have the same signature because the API of the engine is always going to be the same, in the sense that I just want to know what the estimated score or rating will be for this with respect to user ID for this movie. So this is always going to be the same. Whether you pay attention to the movie or to the user, you could fake exactly. Maybe perhaps something else that I didn't mention or maybe briefly mention is that all of this is looking at the column-based approach, which is the collaborative filter. Maybe it makes sense to write a similarity function to compare two movies. Because I think that what is it? There's a genre field for the movies, for example. Things like that. Does that make sense? Okay. All right.
It's going to be a bit of a mess to try and sort out the admin page.
Yeah, I know.
I'll see what's on there now.
Oh, okay, just type them down there.
Yeah. Do you mind?
Oh, yeah, for sure.
You do mind?
Sorry, I also didn't know the password.
Oh, Pycon. Sorry.
So I'll go to the, after Amber says this, I'll go to the admin page and show the leaderboard.
Okay, so, sorry to interrupt for 1 second. Here at the bottom of the page here, I have added the links, the URLs to the surveys. So it's just an evaluation survey for you guys to tell us, how we did, what we can improve, et cetera, et cetera. There are also, I don't know if you saw some signs out front all over the place that have QR codes. The QR code have, I think, the SurveyMonkey URL built into it. So you can also do the survey later if you want. Just they asked us to post these links for you. So you can have a chance to do that whenever you want. Thank you.
How's it going? How can we help? Okay, let me grab on the chair. No, that's fine. Am I stealing somebody's chair? Probably. I just want to make sure. Oh.
So what happens, similar more way to
Okay, so hopefully at this point you're making some progress toward your estimation function. We have 15 minutes left. The point is not to get a score again out of this. What I'm going to do now with Zach's help is to just put up the leaderboard over there, and hopefully if you have a score, whatever that might be, it doesn't matter. You can submit it using that trick that we showed you before. And then we'll take a look at that. It'll be just for fun, but basically the idea is that like we were doing, a few of us with some teams, is to discuss how you can iterate over these versions and maybe look at a different similarity function or even a content-based idea. So let me go to here, and I think I just need to do admin, right?
Yeah, /admin.
Okay, and /admin will.
Not a lot of scores out there yet.
Yes, not a lot of scores. So many of them are still not submitted, but I think this will also show the names for the people that were working on the questions notebook on their own, right? So only pay attention to the team names. If you've made up a team name, you'll be able to identify yourself. So post that and let's tell us about how you did, and hopefully within the last 15 minutes that we have, we can get someone up to maybe quickly talk about what they did, or maybe they found something surprising that gave them a good boost in the score. Okay? All right.
When they submit a score and we could show the code that they wrote, click on the notebook, but they have to save it first. Make sure they save the notebook.
They have to say that.
Yeah.
Sorry to interrupt. One more thing I should add is that once your score is submitted, we'll be able to click on the team name and it'll automatically show your code. And we'll be able to show your code to everybody else here. If you're comfortable with that, you can say no. But for that to work, we need you to save the notebook, because if it won't reflect in real time. So we need you to hit save once you're done and submitted, and then we'll be able to show it up here. Okay. This is working fantastically.
Oh, I'm blown away.
This is awesome.
Really?
You need to open source this thing.
Yeah. Yeah, people are really engaged, actually. I was surprised to see that.
Okay. So let me see if I can get the screen back on. So let's see if we have any submissions in the leaderboard. I'm just going to refresh this. We'll see some scores. I see a one.
Someone hacked this.
Just for fun there. Okay, certainly.
Very clever.
So one thing I didn't mention, and I didn't mention this on purpose, you do have access to the test data set, right? And you can even return a scalar into the post, right? So you can say that your RMSE is 0 and we'll believe it. So this is not very sophisticated. But it seems that the lowest one is that one, use score name. Is that somebody's team? Okay. So how about we have you guys, if you agree, let's take a look at. Did you save the notebook?
Yeah.
Okay, cool.
It's literally taking the average of the two estimates, the row and column average.
Okay. Okay, that's cool. So it's. Is it down here at the bottom? Reco.
Was that it? I think it was just.
This is the one, right?
Yeah.
Estimate 3. Okay, so Testament 3 is their submission, and apparently they're looking at. Okay. Oh, okay. So this is cool.
Estimate functions.
Right. So this is one of the ways. This makes perfect sense. It's fine. So this is one of the ways in which you can combine the opinions or the estimations of several reco engines or of several algorithms or techniques. And this would be labeled under a hybrid. It's a perfectly valid hybrid. It is linearly combining two estimations from two different estimate functions. And you could see a more elaborate case of this, or the evolution of this being something like a voting scheme in which you pay attention to a particular function in some situation and you pay more attention to another estimation in another situation. So this illustrates one way in which you can mix and match, and it's perfectly valid. So thank you for that. That works. Okay, so I'm glad we had a winner. So thank you for choosing our tutorial. We hope that you've enjoyed it. We will stick around to address more questions and to go through some of the other estimate functions that you're writing in the context of the mini challenge. So I think that should be it for now. Thank you so much.
Yeah, thank you. It's okay.
I don't know where the survey is.